Hi, welcome to this video series on cryptography. Today I'm going to talk about a practical problem. The problem is pretty simple to state. We are having two tables. The goal is to perform a database join between these two tables. However, we should not exchange the data, okay, between the participants. Okay, here we have two participants, Alice and Bob. Alice has a table of social security numbers, for example, which has 3 entries in this table, just for demonstration purpose. And Bob has another table. It has social security number together with salary, okay, maybe hourly salary, something like that. And what is the goal? The goal is to perform a database join of these two tables, and in the end compute some useful knowledge, okay, from this data. For example, what is the total salary of employees who are present in both tables? So if you look at it, it's simple. If the data is unencrypted or exchanged between Alice and Bob, they will simply do a regular Oracle database join or any other database join, and then they will be able to tell right away that the answer is say here 35, right? Because social security number 1 and 5 are shared between the tables. So all they have to do is just add 25 and 10, and the answer is 35. Okay, done. But the challenge though is that how are they going to compute this total salary if they are not allowed to exchange the social security number nor the salary? Okay, so Alice could be one web service. Okay, maybe a web service owned by one particular company, and Bob could be another web service owned by another company. They are not allowed to exchange data due to whatever policy. Okay, so how can we now compute some useful knowledge about this data without compromising privacy? Okay, so or state in other ways, we want to reduce the exposure of data, okay, by doing computations on ciphertexts. Okay, you may say, well, why not just have a common key between these two participants and they will be able to compute. Nobody else can see the traffic. That's not the point of this session. The point of this session is neither Alice nor Bob should be able to have any knowledge about the total salary, nor any information about how many of the entries in the social security numbers are shared. For example, in Alice table, we have 5 and 1 social security numbers, right? These two. And they're also present here. That knowledge should not be exposed to neither Alice nor Bob. So it's kind of private database table join, means no knowledge is leaked about the social security numbers or salary in this case. Okay, and when I say no knowledge, I mean you want to reduce amount of knowledge. Okay, that's what I meant. So how do we approach this problem? Okay, in the previous segment I talked about how to compute intersection of two sets. Okay, if Alice and Bob exchanged the encrypted versions of social security numbers using commutative cipher, then they were able to deduce how many elements are shared between Alice and Bob in terms of the first column, right? Because the first column we can treat it as a set. Alice has a set of numbers, Bob has a set of numbers, social security numbers. Then they can just perform a commutative cipher using, for example, Bullock-Hellman algorithm that I talked about. That will tell us there are 2 elements that are shared. But now in this session, I'm going to take it to the next step. Okay, it's not enough to just know there are two employees that are shared between these 2 tables. We wanted to compute the total salary. Okay, that's what I wanted to talk about. So how do we approach this? Well, this problem is not that simple. There are multiple challenges here. We don't want to expose the data to anybody else other than Alice. Well, Alice wants not to expose her data to Bob, Bob vice versa, and not to eavesdropper. So how do we handle it? Well, we can use the idea of Bullock-Hellman cipher first to compute how many items are shared between Alice and Bob in terms of the social security numbers. Okay, and without explicitly knowing what are the shared items, we can somehow find out that there are 2 items in this case are shared, and then we will use a special cipher called Paillier Paillier encryption scheme that will help us to sort of do computations on the ciphertexts. Okay, that's basically at a high level what I'm going to talk about. So, so let's get straight into the problem now and quickly run the program, show you the output, and then I will talk about the details of the algorithm. Okay. So I programmed this whole system myself in Python. So it's not a perfect cryptographic implementation, just for proof of concept, just to show you the idea that how you can compute on ciphertexts. Okay. So we have alice secrets, right? Alice has a bunch of social security numbers. It's not the same as what you saw on my problem statement, but it doesn't matter. A bunch of social security numbers she has. It's basically a table with 3, 5, 6 items, right? And what about Bob? Bob also has a bunch of social security numbers and corresponding salaries, okay? And you probably noticed that 135749, right? Here it is 397. So the items that are shared between Alice and Bob, I can just copy this for a moment, okay? So that we can quickly see on one view what is shared between Alice and Bob. Oh, I'm sorry. I have not gotten the permission to edit in this page because my other page has the permission. Okay, anyway, so we can quickly compare. It's 357, right? 357. Yeah, 3, 7. Okay, so it's only 3, 7, and 9, right? 3, 7, 9 are shared. So what about the salary now? The salary is basically you just add this one and this one and this one. So it should be 35, right? 13 plus 10 is 23 plus 12 is 35. So let's run it. Okay. So I'm using a public key crypto system also. Therefore, key generation part is a little slow, as I mentioned here on my log statement. But you know, in practice, you generate key only once for public keys usually, or not that often. So what you see here is very interesting. I will talk about the log message details, and the answer is important for us, of course. So answer is 35 as expected. Okay. So how come Alice and Bob were able to compute the total salary? Okay. So how do we do this? This is basically the idea of combining commutative cipher. Okay, so I'm combining two different algorithms. Okay, one is the commutative cipher algorithm, right, that I talked about in my other video, that allows us to compute. So what is the common set of elements between two tables? Okay, and then I also use a Paillier encryption scheme. Okay, I'm not sure I am pronouncing his name correctly, but anyway, apologize for that. A Paillier public key crypto system, right? So these are the two crypto systems that I am using in this algorithm. Okay, so let me now dive into the details and show you step by step what's happening. So from Alice's point of view, what does Alice have? Okay, Alice have bunch of social security numbers, right? She has a table which has social security number, I don't know, just some numbers, 3, 5. Let me be consistent, maybe that helps. It's 3, 7, and 9. Okay, 3, 7, and 9 are common rather. So let's copy in this space so we can do exactly the same our program has. So Alice has numbers 1, 3, 5, 7, 4, and 9. Okay, this is the data Alice has. Okay. Okay, we can get rid of this now. What about Bob? So Bob has also something similar. So Bob has another table. What are the things Bob has? Bob has another table of social security numbers and the salaries. Okay. So basically, this is the scenario for Bob. He has social security number 9 with the salary of 13, social security number 3 with the salary of 10, 6 with salary of 25, and then 7 with salary of 12. Okay, so what is the first step in this process? So the algorithm goes like this. Both Alice and Bob will use a commutative cipher based on the Bullock-Hellman algorithm that I talked about. Okay, so Bullock algorithm is Bullock-Hellman, or I will just call it PH to be short. What is the first step Alice and Bob do? They both agree on the algorithm, right? The PH algorithm is the algorithm they agreed. What Alice will do is she will hash her messages. Okay, what are the messages she has? Basically, a bunch of social security numbers, right? By the way, I already mentioned to you earlier in my other video that just sending the list of hashes will not be secure, because Bob can compute the hash of all the messages he has and then just compare the hash, and he will know what are the common items. Okay, so that's not good. So the first step now, let's talk about the algorithm. Okay, algorithmically, what are the first things we will do? From Alice's point of view, Alice will, let me call this step 1, right? Alice basically computes hash of her messages, okay, her social security numbers. That's what she does first thing, okay? And then what she's going to do, she's going to apply Bullock-Hellman cipher algorithm on her data, her hashes, right? Let me call this, what is the output you get out of hashing? You get digest, right? Message digest, okay. So once this is available, she will apply, step 2, apply PH algorithm, right, on her digests, okay. So she will get now a list of ciphertexts, okay. That ciphertext, she will send it to Bob, okay. Send the ciphertext to Bob. So Bob can't do much with it because it's encrypted using a PH key, which is a private key. Only Alice knows, okay. So now Bob has a list of ciphertexts from Alice. Symmetrically, Alice does something like this. Well, Bob does that symmetrically, to be more precise and correct. Bob does same things, okay. So I will just say do the above steps, right, on his data. So he does the step 1, 2, 3, and then what does he do? He also sends the ciphertext to Alice, okay. But now Alice cannot do much either with that data, okay. So what data I'm talking about? His data means just the social security number, to be more precise, on his SSNs. Only social security numbers are exchanged, and the encrypted versions are exchanged. So what will Alice do next? Alice will take the, now let me go back here. What is the next step for Alice? Alice will go and double encrypt the data that Bob sent to her, okay? So what is the next step now? Let me write it here. Alice, because we are still in Alice. Double encrypt, okay? Double encrypt. Why do I say double encrypt? Because she's going to apply, she encrypts the SSNs of, I must say, she encrypts the encrypted data, right? Because Bob encrypted the data, encrypted SSNs using her PH key. That's what she will do. What about Bob? Bob does the same. It's basically regular Diffie-Hellman double encryption, right? Bob does the same. Okay. So let's see. Step 5. He encrypts the encrypted SSNs using his PH key. Okay. So the beauty of the commutative cipher is that at this point, both step 4 and step 5 will give some interesting insights, okay? If the social security numbers are shared, meaning they are present in both database tables, the output of step 4 is equal to step 5 whenever the same social security numbers are present in 2 tables, okay? That's what I talked about in my other video when I discussed the details of a commutative cipher, okay? So now they have found out Okay, they exactly don't know which social security numbers are shared, but they know some of them are shared at this point. There's one more step I must clarify that. So, and then see step 6. Okay, he sends the data. He sends this data to Alice after some kind of random permutation. Okay, meaning she just shuffles the data after shuffling it. Okay, the reason for shuffle is that otherwise Alice will know exactly what items of which social security numbers are shared with Bob. So Bob will avoid that by just shuffling this data. Okay, now let me go back to Alice. So Alice will now be able to easily compute the shared data. Okay, in step 7, shared, all she does is basically takes the intersection, right, between the data she got from step 6 and with step 4. Okay, intersection of step 6 and 4 and step 4. That's basically it. Okay, so remember in step 4 she's encrypting the SSNs she received from Bob. So basically the double encryption, right? That's why I said double encryption. So okay, so in step 7 she would know exactly, this is important, step 7 she knows exactly the list of social security numbers. She can't point out back to which lists of which SSNs are shared. She knows a list of social security numbers, but they are all in double encrypted form, so she can't do much with it. Okay, so what is that she will do next? Okay, now comes the trick. Remember, Bob also has the salary data. So Bob encrypts that salary data, right, and actually send that salary data as part of I must have said here, you know, when I said do the above steps, on SSN, right? This particular step, Bob actually has also encrypted his salary data. So let me clarify this a little bit here. Okay, Bob encrypted salary data using another key. Okay, this is the Paillier public key system, okay, which I will talk later in another video, but at this point we can assume it's a black box for us. Paillier public key system. Okay, so he encrypts all the salary using a public key. Only he knows the corresponding private key. He encrypts those. Okay, and he sends the encrypted data to Alice. Okay, Bob sends encrypted salary to Alice. Okay, Alice can't do anything because she doesn't have the private key. So, but why is Bob sending that to Alice then? Well, remember now the step 7. Step 7 has already given the common list of social security numbers in encrypted form. All Alice has to do now is take the output of step 7, right, and perform a join with the table that Bob sent at the very beginning. Remember, Bob sends encrypted social security numbers together with encrypted salary. Okay, so all Alice does is just perform the join on two tables of encrypted data. Okay, that's basically it. So the final step is basically, well, almost final, not exactly there. Let's see. Alice in the step 8. Okay, Alice computes. Okay, I must have put Alice here. Alice computes join, but this join is, remember, on encrypted table. Okay, between Bob's social security number and Alice's social security number, and those are also encrypted, but it must be the same because of the commutative cipher. Okay, once that is done, there's one final step for Alice. Alice is going to apply one of the multiplicative properties of a Paillier cryptosystem. Okay, she's going to multiply all the ciphertexts, and then she's going of the salary. Okay, so what is she going to do? She's going to multiply. Let me write it here. Okay, and the next step, right? Step 9 sort of multiplies encrypted salary data. So why is this? Why would you ever multiply encrypted data? Well, it turned out that if you multiply salary data or multiply any data encrypted using Paillier crypto system, when Bob receives that encrypted data, he can just decrypt that. So what is going to happen now is very simple. Bob is basically, as a final step, Bob decrypts the multiplied ciphertext. Remember, salary itself is still encrypted, but when Bob decrypts that, the salary is made public. Okay, meaning not the individual employee salary, but the total salary. That's the property of this crypto system. Okay, so let me clarify that again. Homomorphic property of Paillier system is the property that we are using. Okay, homomorphic property. So in the Paillier system, encryption of, if you take encryption of, say, a message M using a public key E. So homomorphic property. What is homomorphic property in Paillier system? If you multiply encryption of a message M1 with encryption of message M2, remember encryption of M1 using a key E will give you some gibberish, and similarly encryption of M2 with the same key E will give you another gibberish. You're multiplying these two gibberish, but then you send this gibberish to Bob. Bob has the corresponding private key to decrypt. So what is he going to get out? It turned out that in this Paillier system, it has a nice property that this is nothing but M1 plus M2. Okay, this is the homomorphic property. In many cases, this property is not desired, but in multi-party computation, this property is often desired. Okay, so essentially, Bob gets to know the total salary, and then he will just publish it to Alice, saying this is the total salary. Okay, so in this process, neither Bob nor Alice learned the individual employees, more information about the individual employees. Of course, Bob knows the salary of social security numbers and the corresponding salary, but he doesn't know that employee number 3, salary SSN number 3, SSN number 7, and 9 are also present in another database. Okay, that knowledge is not leaked to Bob. Okay, similarly, Alice doesn't learn the salary of employees that who are present in another table. Okay, so to sum up this discussion at a very high level, what's happening is we have two crypto systems. Okay, one is the commutative cipher crypto system that allows us to compute and identify what elements are shared between the two sets. Okay, we don't exactly know the elements, but we do have a ciphertext or a list of ciphertext rather that correspond to shared items. Again, we don't know the shared items, but we do know the ciphertext of the shared items. Okay, this is commutative, same ciphertext present on both sides. Okay, and using that data set, we can just simply do a join on the table Bob sent to Alice. So Alice would know exactly what ciphertext to multiply. Okay, and that's what you're seeing here. She is multiplying the ciphertext and then sending that multiplied result to Bob for decryption. That's basically what this whole private compute is. Okay, what I did is essentially let me clear this. What I essentially did is send this table in an encrypted form, okay, with two different keys. The first key to encrypt the first column, second key to encrypt the second column. But Alice can't do anything with it because she doesn't have the keys, matching keys. Alice has another key to encrypt her data, and Alice exchanged the encrypted social security number with Bob. Bob exchanged encrypted social security number. They both have the same cipher, okay? Same cipher is used for encrypting the social security number. They do double encryption just to make sure to get the common items computed, okay? And then they just do a join with the salary. Salary is also encrypted, but then they apply Paillier encryption system to multiply the ciphertexts. Alice does that and send that to Bob. Bob does the calculation of decryption and then has the salary computed. Okay, that's basically it. And now I'll show you the implementation details very briefly. Okay, so implementation wise, I have this Paillier crypto system, more or less black box. I implemented most of the functions except some basic prime number generation functions I used from other libraries. I will talk about Paillier crypto system later. It's a public key crypto system similar to RSA, you can imagine, but it has the homomorphic property that I talked about in the demo. Okay. I also mentioned about the Pollig-Hellman cipher, right, which is another cipher that I talked about in my other video that allows us to do the double encryption. And the beauty of this algorithm is that if the same data is encrypted using two different keys, it doesn't matter which order you apply the keys, you will get the same cipher. Okay, what I mean by is that is this. Suppose you have a encryption of this, right, and then you encrypt this again, say using another key. This is same as encrypting, so it doesn't matter what order you apply the key to the message. Okay, you will get the same cipher. Okay, that's basically the idea of the Paillier crypto system. And this is used to identify the common elements shared between the two data sets. And then we use the Paillier crypto system to encrypt the salary data. Bob is using that. And then Alice is basically, once Alice computed the join, she will multiply all the ciphertexts and send the multiplication of ciphertext to Bob. Bob would apply decryption and get the total salary. Okay, so let's quickly walk through the high-level idea. If you wanted to implement this yourself, it's easy. So I will show you the details one by one. Okay, what I have is basically a safe prime from RFC 7919 because I'm implementing the PH algorithm myself, right? Alice first, as I said earlier during the demo, Alice computes the hash of her secret IDs, right? Once that is done, she generates a Bullock-Hellman encryption key. So the key generation generates encryption and decryption key, but in this case, we never decrypt the data, so we will only need encryption key. Somewhat weird, but that's the nice property. And then Alice encrypts her digest of IDs using the Bullock-Hellman key X, and then she sends that to Bob. So Bob has the encrypted list of digest from Alice. Bob does similarly, converts his IDs into digests, social security numbers into digests. When I say ID, you can imagine a social security number. And then Bob also generates encryption of the digests, right? Similar to Alice. And now comes the Paillier crypto system, okay? Bob applies Paillier crypto system, so he has to generate a public key and a private key. But then Bob encrypts the salary using his public key, okay? This is important. Bob encrypts the salary data using public key. And then Bob sends out now two things. One is the list of encrypted social security numbers, or IDs, I call it here, and the corresponding salary data encrypted using a Paillier crypto system. Okay, public key was used. And then what is Alice doing? Alice is taking the incoming data. She double encrypts the digest, only the digest. Okay, the ID or social security numbers ciphertext is double encrypted. And then what is Bob doing? Bob also doing the same. Bob receives the ID from Alice, right? And then he double encrypts the incoming IDs, which are all encrypted anyways, using his PH key. that he already generated, right? Okay, at this point, Bob rotates the IDs and then send it to Alice. When I say rotate, I mean shuffle. Okay, Alice will now compute the intersection of doubly encrypted data sets, basically the social security numbers sent by Bob to Alice and vice versa in encrypted form. And now the both basically contains a collection of social security numbers that are shared between these two tables. But again, both is not plain text, okay? Both is basically collection of ciphertexts, but they are the same whenever the social security numbers are the same, okay? So what is the next thing? Now this is basically the regular join, right? You look at the corresponding salary data to add. So he's basically computing the join. And then, as I said earlier, and now he's going to do multiplication, right? He multiplies all the salary data that Bob sent to Alice, basically the encrypted salary data, right? Bob has encrypted it, and then Alice is multiplying those salaries that match the social security numbers that are shared. That's the shared IDs, right? Once the shared IDs are available, she does the multiplication with the incoming salary data, also in encrypted form. This is basically modulus of n square, because Paillier cryptosystem works with a group of zn square, right? This is basically what Paillier cryptosystem is. I'm not talking about it in this video. We will talk about it later. So, and then in the end, it's very simple. Now, Alice is sending the product of ciphertext to Bob. Bob decrypts that because he has the corresponding Paillier private key, and then he publishes. Okay, that's what you're seeing. So there's a lot of key exchange. Well, not exactly key exchange. A lot of encryption and decryption. But the beauty is that there's no key exchange. You're basically only exchanging ciphertexts, and you're doing computing on the ciphertext. And at a high level, you're basically preserving privacy, because you're not sharing the knowledge about the salary or the social security number. Of course, this implementation has nothing to do with those two data sets. You can apply it on any other similar scenarios. Whenever you have situation where you cannot share data, but you're allowed to do computing on the ciphertext, then you can apply this technique. Okay. As I started showing you, for the data set we are given, the salary, the total salary of the shared social security numbers is $35. Okay. So let me quickly wrap this up. The log is very useful. Alice converts a list of IDs or social security numbers into digests. And then Alice generates a Bullock-Hellman encryption key. And then she encrypts the IDs and sends the IDs, the hash of the IDs, I must say, to Bob. So Bob has Alice's data. Bob also has his IDs, convert into hash of them, and then generate an encryption key, a Bullock-Hellman encryption key, encrypt the IDs. Okay, now Bob also has to encrypt the salary data, remember? So he generates another key, Paillier public private keys. Okay, well, that was a little slow because key generation is done only once usually, so it's okay to accept a little slow. Bob sent to Alice Paillier public modulus, because remember, Alice has to do multiplication later. She needs the mod n square. Okay. Bob computes the encryption of all the salaries using Paillier cryptosystem, and send two things. One is the list of encrypted IDs, right? PH encrypted IDs, and the list of corresponding Paillier encrypted salary data. Okay. Now, what is Alice going to do with it? Well, Alice is going to double encrypt the data that she received, only the IDs though, not the salary part. Okay. And then Alice, I think it should move a little bit. Okay. So we are here. Alice generates the after Alice computes the double encryption, Bob will send to her the his list of double encrypted IDs, right? That's basically what Bob does, and then Alice will compute the intersection of two double encrypted IDs, right? And once that is clear, she will just go ahead and find out the corresponding salaries that are matching the IDs. Remember, the IDs are encrypted, double encrypted rather, once you have the matching. Salaries are also encrypted, but that's fine. Alice is just going to multiply all the salaries and send to Bob. Bob decrypts that. Because of Paillier's homomorphic property, Bob will be able to calculate the total salary. So together they computed the total salary of employees that are shared between two different databases. Okay, this is basically the idea of a private join notion. Okay, so you have two tables, you are doing a join without sharing the data. Okay, that's basically the idea of this